Hello everyone and welcome to The Biggest Ideas in the Universe. This is our second Q&A video. I'm your host Sean Carroll and we'll be talking about the questions that came in after the second video in the series, the second idea that we were talking about, namely change, which was really about calculus. And I have to say it's been very heartwarming to see people watch the videos, respond to them, even if they're about, somewhat abstract technical topics. We have started very, very gently with conservation and change. We're going to ramp up as the videos go on, but the same idea is the basic philosophy that it's for everyone. Literally everyone can follow these videos if they want to. There's no prerequisites presumed, but there's an interest presumed. You have to be willing to think about it and see where that goes. And so as a treat today, we have a little bit of a technological improvement. Watch this. That's right. We actually now have a dark background and light writing on the notepad. This was a request several people made, so we're trying it out. Let me know how it goes. I will take input on this. The one thing that we needed to do to make that happen was I was using a program called Notes Plus, which on a MacBook Pro, on an iPad Pro with the Apple Pencil. Here's my Apple Pencil. And it works very, very well for note-taking. Notes Plus is great. Helps, you can export the PDFs very easily to your laptop or whatever. But of all the different background options, they were all light-colored. There was only for writing in dark pen on light backgrounds. So this one is called Notability. I've switched programs to Notability. Another great program. You can look it up if you're interested in doing this. And this one has dark backgrounds. Now, this particular background is sort of almost a fabric kind of theme to it, but hopefully it'll just be in the background and be a dark grayish blue, and that will be good. You can do totally black, but that just seemed less aesthetically pleasing to me. Okay, there were a large number of questions. I'm not going to get to nearly any of them. I'm going to make zero effort to specify who asked each question. Sorry about that, but you still get the warm feeling from having asked a question. Many of the questions overlap, so I'm sort of grouping them together in themes. And also, between you and me, given that I've actually recorded a couple of the other videos coming up, the videos are getting long. I don't want the videos to be long. I want them to be shorter and accessible, so I'm going to try to keep things a little bit shorter. We could ask questions forever, right? But I'm going to try to focus on some of the best ideas. Oh yes, I forgot to say that I've improved, I think, my green screen technique enough where I do not necessarily need to wear a red shirt just to make it work. Again, we'll see whether that works or not. Okay, on to the questions. What do we have? The first question, it's a basic one. How do we get from rate of change of position over time to the actual position over time? How do we get from velocity, which is rate of change of position over time, to position over time, x of t. So, and I put this one in there explicitly because, in principle, I answered that one in the video. That was part of what I was trying to do. But I'm extremely well aware that just because I think I've answered something doesn't mean that everyone thought it was perfectly clear the first time. So let me just say a little bit about the intuition behind here, okay? The simplest possible way of thinking about it. Imagine that you're in a car, and this car is so good that it can accelerate from 0 to 60 miles an hour, for those of you not in the United States, in literally 0 seconds. And furthermore, it can brake in literally 0 seconds. So if you plotted the velocity versus time of this car, velocity versus time, okay, it's 0, and then boom, it's 60 miles an hour, and then boom, it's 0 again, right? And furthermore, imagine this went on you drove for 1 hour. Well, pretty clearly you can figure out how far you went. In fact, you can figure out your position as a function of time, right? Just from that, if I plotted, here is your position x as a function of time, t, put a little arrow here, then your position is you're not moving, and then you're moving at some constant velocity for an hour, 60 miles an hour, and then you stop moving, okay? That is the answer. I mean, that's just sort of intuitive. We sort of know that. That's what it means to be moving at 60 miles an hour. The point is, the slope of this curve, x of t curve, is the velocity, And if you think about what it means when we said derivatives and integrals, derivatives are the slopes of curves, integrals are the area under the curve. So when we say that the derivative of x is v, that kind of looks like it makes sense. Over here, the slope of the curve is 0, and indeed v is 0. Over here, the slope of the curve is some constant value that is not 0, and indeed v is some constant value. Over here, again, you're back to the slope being 0, and indeed the velocity is 0. So it does in fact look like you can go this way, v equals dx dt. Velocity is the derivative of x over time. But also intuitively it looks like you can go the other way if you really sit and think about it, right? The velocity popped up very, very quickly to a constant value. And if you think about it, what we're saying here is that x is the integral of the velocity. That's how you're supposed to go from the velocity to the position. So when the integral is the area under the curve. And when you're in the position here where you're not moving at all, where the velocity is 0, there's no area under the curve. And indeed, x equals 0. There you go. Once you come to up here and you sort of divide the area under the curve into these little regions and you add them up, okay, there's a little bit, there's another little bit, and they accumulate over time. What you would expect is the area under the curve goes from 0, it goes up by a little bit, and a little bit more, and a little bit more, and a little bit more, and then it stops going up once the velocity goes back down to 0. Indeed, that is exactly what the curve of velocity of x versus time looks like. It starts going up at a constant rate because you get more and more area under this curve, and then it stops going up when the velocity goes back down to 0. So it goes both ways. X is the integral of the velocity times time. Over time, I should say. That's what it means. Again, the symbols, the equations are not what matter. We're not going to try to remember them, but that is what it means. So this is how you should think of it whenever you have a physics question. Like whenever you don't understand some concept that the professor thinks that they've just taught you, you should say, well, let's simplify it to like the simplest, most straightforward, dumbest example I can think of. Surely I can understand that. Maybe that gives me enough understanding more generally. The point being, of course, that in other much more general situations where the velocity is not just 0, 60, and then 0, it would still be the case that the velocity is the derivative of x, and x is the integral of the velocity, but it would be harder to go back and forth mathematically, but you could do it. Okay. Wanted to get that out there because this is, like I said, it's for everybody. Good. Now we're getting a little bit trickier in the questions here. Zenos paradoxes. Remember Zenos paradoxes? One is, I'm going to forget, he always had colorful characters like Achilles and the tortoise or whatever, but one is, he claimed that motion was impossible. This is Zeno of Elea. This is an ancient Greek philosopher. He says motion is impossible because, look, let's say you want to go in x, and by the way, parenthetically, once again, this is something that scientists and mathematicians do all the time. I was just drawing some plots where t was the horizontal axis, and look, x was the vertical axis. Now I'm going to draw a plot where x is the horizontal axis. Get used to that. This is part of the game. Anyway, this isn't really a plot here. This is just an illustration. So you want to go from your starting point at x equals 0 to some finishing point. Let's just call it x equals 1. But Zeno cleverly says, okay, guess what? To go from 0 to 1, you have to go halfway there. So you have to reach the point x equals 1/2. And to go from 1/2 to 1, you have to go halfway in between that. So you have to eventually reach the point x equals 3/4. And then you have to go halfway between that, so you have to get to x equals 7/8, and so forth. You can keep going in smaller and smaller increments. And Zeno points out correctly, there are therefore an infinite number of intervals that you have to pass to go from 0 to 1. Therefore, you can't go through an infinite number of intervals, therefore you can't get there. You can't get there from 0 to 1. We all know this is crazy talk because we've seen people go from one point to another. Motion is in fact possible. What is the resolution to this apparent paradox? And so the question is, does calculus help you understand this? I think in some ways it does. I would say that calculus helps explain what is actually going on. I don't think that calculus is necessary to explaining this kind of paradox. From the point of view that we've been talking about here, I mean, the way to think about this is Sure, you have to go from 0 to 1/2, from 1/2 to 3/4, from 3/4 to 7/8, etc. But you don't have to spend equal amounts of time doing that, right? I mean, if you moved at a constant velocity, you would spend half the time going from 0 to 1/2, a quarter of the time going from 1/2 to 1/4, an eighth going from 3/4 to 7/8, and so forth, right? So the velocity would be the same, even though you have to spend even though you have to pass an infinite number of intervals, you have to spend less and less time doing them. So not only does the distance that you traverse go to 0 as you get closer and closer to your goal, but the time it takes to traverse that distance goes to 0. So overall, if you say how much time will it take you to go from 0 to 1, it's a finite amount of time. You can formalize this using calculus. In fact, the idea of an infinite series is a big part of calculus. A big part of calculus is saying that some function x can be written as some function f0 of x plus some function f1 of x plus another function f2 of x, where these functions become smaller and smaller in the regime where you care about. So plus ... an infinite number of these functions you have to add up. This is part of the idea of approximating by something that looks like just an approximation, right? A finite little bit. But when you take the limit as some parameter goes to 0, this approximation becomes exact. That is what calculus is all about. Okay. Next question was, can you calculate the derivative of a fractal? I'm not going to write all the questions, all the words to all the questions. What about fractals? So fractals are curves that have sort of an infinite amount of structure in them. So a famous fractal, for example, draw a straight line, then draw a triangle so that the one side of the triangle takes up 1/3 of the line, right? So this is 1/3, 1/3, 1/3. Then draw another triangle, other triangles that have that same property for all the lines you've drawn, then draw other triangles that have that same property for all the lines you've drawn, and do that literally an infinite number of times, okay? So what you would find is that this is a curve, but it is not a smooth curve. This has some name, someone's snowflake, okay? It's not a smooth curve. So mathematicians, of course, have classified what that means in wonderful detail. No, you cannot take the derivative of a fractal. A fractal is not something that has a limit to these questions, right? I mean, there were some grumbles in the questions, and I anticipated, if you watch carefully the video, I said, look, the mathematicians are going to be outraged. The mathematicians were outraged in the questions. That's okay. The point is that we were making some assumptions and not explaining them, not listing them explicitly. One is that the curves that we're dealing with are smooth. And one feature of that is that the limit exists to these kinds of questions you're talking about. So if you look back at this curve we drew of velocity versus time, the limit as you approach the acceleration point, right? The velocity is 0 before the acceleration point. The velocity is 1 or 60 miles an hour after the acceleration point up here. If you approached the velocity curve, if you approach that point on the velocity curve from the two different sides, you would get two different answers. So the limit as you approach from two different sides gives you different responses. There's a discontinuity in the curve. Technically speaking, you could not differentiate this curve, v of t. You can differentiate this curve, x of t. Well, you can't quite differentiate it there because it's not smooth either, but that's okay. We sort of approximate it or think of it as a step function, as something that just suddenly changes its value. Philosophically, this is a difference between mathematicians and physicists. Physicists say, okay, I know I'm cheating a little bit, but I know it's going to work too. I'm going to get on with my life and solve some physics problems. Mathematicians go like, no, cheating is exactly what we're here not to do. We should do better than this. And you need both. There's not one way of doing things that is correct and the other incorrect. They work together. But I'm more on the physics side in my own approach to these issues. Okay, here's a tough question. Why is integration, taking the integral of some function that someone hands you, harder than differentiation, taking the derivative of some function someone hands you? This is a true fact. When someone gives you a function, f of x, you could take its derivative, df dx. You could take its integral, integral of f of x dx. This is the slope at any one point. This is the area accumulated under the curve. But when you sit down to do that, when you actually go through the math, run through the equations, differentiating functions is easy. I mean, you can do it. There's very few functions out there that you cannot just differentiate and get an exact, what we call an analytic answer to. Integrating is really hard. It is very, very often the case that realistic functions that we have in physics and math cannot be exactly integrated. That's why you put them on a computer, let the computer do all the work. So this profound philosophical question is, why is that true? After all, they are inverses of each other. We just showed that with our simple little example, right? The derivative of the integral is the original function. So I mean, technically the answer is I don't know exactly why. I do not have a nice, clever sounding answer for why differentiation is so much easier than integration. What I will note, though, is that it's not at all an unusual state of affairs. It is very often the case that you have two operations, two mathematical operations, where doing it one way, there's an inverse, you can do it the other way, but they're not equally easy. Think about a very different, simpler problem, which is just factoring one number into its prime factors, right? If we imagine, just to simplify, that we're given a number, n, that's our number, and someone promises us that it is the product of two prime numbers, a and b. So a is a prime number, b is a prime number, n is their product. There's two questions you might ask. One is, given just n, can you figure out what a and b are? That is a very hard problem. That takes time to work through all the different possibilities. On a computer, if n is really, really big, this could be an impractical question to ask. Whereas, if people give you a and b and say multiply them, it's very easy to multiply them and get n. It doesn't take any time at all, relatively speaking, right? A pocket calculator can do it. So they are inverses of each other, these two questions. Given n, what are a and b? Given a and b, what is n? But they're not anywhere near equally hard. So this is a feature, a feature of mathematical problems more generally, that doing it one way and doing it the other, doing a problem and doing its inverse, need not be equally hard. And in fact, this is the basis of a very famous problem in complexity theory. Complexity theory is the study of how hard problems are. And you can quantify that by how many steps would it take on a computer to solve a problem algorithmically. So there's a famous battle or comparison between P versus NP. These are two classes of, two complexity classes, two classes of different kinds of mathematical problems. P is the set of problems that are easily solvable. And again, I'm not going to go into the details. Sorry for the experts in the audience. The details are that if you can solve the problem in polynomial time, where polynomial means polynomial in the size of the problem that you're giving it, then it's in P. A polynomial can be big numerically, but polynomial functions grow much more slowly than, let's say, exponential functions. So this is classified as fairly easily solvable. NP, the solutions, if you're given a solution, is easily checkable. So from our example of factoring, right, given one number, what are its factors versus two numbers, multiply them together to get the number, it would seem clear that P, the set of all problems that are easily solvable, is way smaller than NP, the set of all problems for whose solutions are easily checkable. But when you want to prove it, it turns out to be really, really hard. So there's a question on the market right now, is P equal to NP? And no one knows the answer. Actually, everyone knows the answer. The answer is no, they're not equal, but no one has been able to prove the answer. If you prove this, that P is not equal to NP, or if you prove that it is, you'll win $1 million. It's that kind of problem. But the point I want to get is not to get into complexity classes, but even though I can't give you a simple, nice, beautiful, clever explanation for why integration is harder than differentiation, you shouldn't be surprised by that fact. it is a general feature of mathematical procedures that even if there's one way of going and there's an inverse to that, they're not equally easy or equally hard. So whether or not that makes you feel better about differentiation and integration, I don't know, but so be it. Okay, there's another question that came up a few times, so let me get it out there on the table. We talk about F equals ma, force equals mass times acceleration. So which mass are we talking about here? You may have been exposed to various different concepts that all go by the name mass. There is the inertial mass. That's what this is. Inertial mass in classical Newtonian mechanics is just if I put a force on the object, how much does it accelerate? The quotient of those two things is the inertial mass. It's basically how much do you resist the acceleration when the force is being acted upon you. That's one thing. So there's inertial mass. There's also gravitational mass. Systems with mass both respond to a gravitational field and cause a gravitational field, and the amount of response and the amount of cause is proportional to the mass. So it is a fact of physics that the inertial mass of an object is equal to its gravitational mass. Newton wondered about this. Einstein wondered about this. We have different explanations for it, but it doesn't matter. These are two concepts that serve different purposes, but they are numerically exactly equal to each other, so whichever mass you want. But then there's something called the relativistic mass. So this comes from the fact that once relativity comes on the scene, things change when objects are moving close to the speed of light, right? Their clocks tick differently, their rulers are different lengths and so forth. And so is it the relativistic mass that goes there or just the good old Newtonian inertial mass? So you should be able to guess, since we're doing Newtonian physics, not relativity, that it's the inertial mass. It's the non-relativistic mass that goes in there. And that's true. But I wanted to bring this up because most modern physicists will never even talk about the relativistic mass. The way that they used to think about it was there's a mass, you could put something on a scale, okay, you could weigh it, and then if you knew the gravitational force down, you could figure out what the mass of the thing was. But then if you moved it close to the speed of light, it would take more and more oomph to push it at faster and faster velocity, so it's as if the mass is increasing. These days, we would say that the energy is increasing, but the mass we define to be the rest mass. So personally, I would never use the idea of a relativistic mass. The only thing that we would ever use is the rest mass. M equals the rest mass. And when you write E equals mc squared, what you're defining is not the total energy of the system, you're defining the rest energy. You're defining the energy that it would have if it were at rest, if it were not moving. That's what E equals mc squared is telling you. So that's what it is for this, but I did want to give you that, even though we haven't been doing relativity yet, I wanted to warn you, like, the definition of mass is not going to change. It's always the rest mass, which is equal to the inertial mass, which is equal to the gravitational mass. Okay. Here's a good question, which is a little bit philosophical, but it'll get us, it will once again prefigure something that is going to come later. Is velocity, which we've been talking about a lot, really an instantaneous quantity? That is to say, can we really define it at a moment of time? So what we mean here is, if you have here's t, here's x, okay? And we say that if you have a curve, the velocity is supposed to be the slope of this curve, right? Clearly, at any one moment, t, there is something called x. If this is t naught, let's say, this is x at t naught, no one has any problem saying that exists at that moment. The velocity is the slope, the rate of change, and there's sort of a slight tension between two different claims. One is the velocity exists at each moment of time. It does. It certainly exists at every moment of time. We could differentiate this curve, take its derivative, and then we would get the velocity at every moment. But the other is, could you really consider the velocity to be an instantaneous quantity? Because if you're saying the velocity is the slope, it's the rate of change, which is, it's the rate at which the value of x of t right now compares to its value in an infinitesimal moment in the future or in the past. So in some sense, you have to know something about the immediate future or the immediate past to define what you mean by the velocity. So the answer is, that's everything I just said is perfectly true. In this way of thinking about it, where x as a function of time is the fundamental thing, which, by the way, is the way that Isaac Newton would have thought about it, then yes, you need a little bit of information around the moment t0 to define the velocity in terms of the position. But there are other ways of doing classical mechanics. You know, we sort of moved back and forth between velocity and momentum. P equals mass times velocity, because if the mass is constant, then who cares? You can use momentum or velocity. There are other ways of doing classical mechanics, which we will get to a couple of videos from now, where you treat x and p as the fundamental things, the position and the momentum, and you treat them as truly independent. You say, no matter what x is, p can be anything. And people say, okay, at one moment of time, I get that. But if I knew what x was doing through time, then p can't be independent of it. And the answer is, yes, it can, but this equation might not hold. That is to say, rather than thinking of this equation as a definition, you can think of it as something that may or may not be true. And then P really has a life of its own. It's really something other than just being derived from the mass and the velocity. But we aren't there yet. So for the purposes that we have right now, x as a function of time really is fundamental. You figure out what velocity is. But I'm just letting you know ahead of time, it's not the only way to go. It's not the only way to think about things. Here's a fun one. We've talked about a whole bunch of historical figures in the development of this, right? Copernicus, Kepler, Galileo, Newton. They lived in very different times. We're talking 1500s, 1600s. Did any of these people, when they were thinking about their science, their systems of astronomy and physics, did they ever invoke God? That's a good question. And the answer is, yeah, sure, of course. This was a time when, no one in the year 1600 went around advertising that they were an atheist. Maybe there weren't any atheists. I'm talking about Western Europe now, with the history with which I know just a tiny bit about. Everyone professed to believe in God, and some people did so, many people did so extremely sincerely. Copernicus, I don't know anything about his personal beliefs, but I know that Kepler was very religious. He thought of his whole system of the celestial spheres and so forth, the ellipses in Kepler's laws, as illustrating the precision and beauty of God's system. Galileo, I suspect Galileo couldn't care less. I'm not saying that he was an atheist. I honestly don't know. Maybe a Galileo scholar will chime in. I think that Galileo just never thought about what God was supposed to do, and certainly wouldn't give God credit or any responsibility in pushing things around in the universe. Newton is the interesting case because, on the one hand, Newton invented classical mechanics, this beautiful system, and I mentioned that in some way, classical mechanics decreases the need for God, because you don't need something to be pushing. You don't need an unmoved mover. Things just move by themselves. That's just what things do. So this argument from a first cause or a first mover that was very popular back in those days, it's not the only argument for the existence of God. There's also the argument from design, right? The argument from design that the exquisite design of nature. Nature is very elegant, very beautiful, maybe even finely tuned for our existence, and to attribute that elegance, that simplicity, and also just the law-like character of motions of things in the universe to God. That's an argument for the existence of God. Why should things obey the laws of physics at all if God didn't make them do that? Newton totally bought that kind of argument. I mean, he said about his own system of classical mechanics, basically God must exist to invent something as beautiful as the thing that I just invented. But it went beyond that a little bit. Kepler, when he talks about the planets going around the sun, he imagined they were going in these beautiful, pristine ellipses. Newton went beyond that, as we discussed. Newton said, well, okay, but there's more than one planet, and here's a planet moving here in some trajectory. Here's another planet moving here in some other trajectory. And I've just invented the law of universal gravitation, so I know that these planets are not just going to be pushed around by the sun. They will also have the gravitational influence of each other on them. So they will not move perfectly in ellipses. And Newton, I don't know whether he worked this out or whether he just intuited it. But he kind of had the feeling that if that were true, something as beautiful as the solar system wouldn't last forever. This turns out to be correct. It wasn't really understood until maybe Henri Poincaré, circa the year 1900. But yeah, the solar system can be thought of as unstable. If things go wrong, planets can be just, launched out of the solar system, and it's happened in the past. So Newton didn't like that idea. He thought the solar system should be permanent. So he said very explicitly that he imagined that God would occasionally intervene, that God would come along, change the velocity of the planets, line them back up so everything was hunky-dory once again. There's no experimental evidence for that. By the year 1800, Pierre-Simon Laplace was, poo-pooing that idea. He probably was just legitimately an atheist. I don't know exactly the details there either, but he certainly thought the idea of using God, relying on God to explain your cosmology and astronomy was a bad idea. These days, in case this was a subtext of the question, most scientists are probably not themselves personally religious, but there are some who are a little bit religious. There are some who are very religious. Very few scientists would invoke God in their science, right, as an explanatory feature of how they talk about the world. I mean, maybe they'll put it to create the Big Bang or something like that. But again, most of us don't really need God around anymore to explain the natural world. Okay. Back to physics. Are there any experimental tests, or could there be, I guess? I wish I were better at talking and writing at the same time. Are there experimental tests of the discreteness of time? I talked about at the very end of the last video the idea that all this calculus stuff relied or presumed that time was smooth, that time was continuous, that there was an infinite number of moments of time infinitesimally close to each other. That's why we needed calculus. If reality were more like a computer, maybe it is, maybe we live in a simulation or something like that, but computers tend to be digital. They approximate smooth curves by chunking forward in discrete amounts. It may be, although we don't know, that the real world is also like that, that time truly is discrete. If that's true, could we experimentally test it? Well, we certainly hope so. I mean, we absolutely hope so. We don't know for sure, but we're absolutely trying. So it's not enough to say, well, maybe time is discrete. What's the experimental test? You need a theory. You need to say, here is how time works, and it is discrete. You can test theories. You don't sort of test ideas, okay? So there might be different ways for time to be discrete and have different experimental consequences. I will mention one place where it's natural to look, which is, I think I mentioned it maybe already, or maybe it's just in my head, Lorentz invariance. Lorentz invariance comes not from Isaac Newton, but in relativity, the idea that how fast you're moving through the universe doesn't matter, okay? If that's true, how fast you're moving in the universe doesn't matter, you know that from Einstein that the rate at which clocks tick will appear different to an observer that is moving fast than an observer that is moving slowly. And if you can move at any different velocity, then you can make the clock seem to be ticking at any different amount, and therefore it doesn't seem like time is discrete. So naively, if time is discrete, there should be some violations of Lorentz invariance somewhere. And these are things that are being tested, so we're looking for them. There's no evidence of it yet, but we absolutely would love to see either evidence for it or evidence that really put very strong constraints on it. Okay, two more questions about the future of physics. We're going to peer into the speculation realm here a little bit. Are Newton's laws, so F equals ma and the others, are Newton's laws completely true? Or are they just valid in some regime? So there's sort of two answers to this. One is no. They're absolutely not completely true. Because we know they're not completely true. We know there's quantum mechanics. We know there is relativity. And presumably will just get worse, right? I mean, presumably as we know more and more about physics, what we learn and what we completely expect, at least, let me put it this way. We probably didn't expect this in the 1800s. But by the time the revolutions of relativity and quantum mechanics came along, and we saw that Newtonian classical physics and Newtonian gravity were both limiting cases that were approximations to relativity and quantum mechanics, the idea that we'll have another theory in the future that is even more comprehensive so that relativity and or quantum mechanics are approximations to them, valid in some regime, became very palatable. So many of us expect that something like that is going to be true. I wouldn't be at all surprised if quantum mechanics is exactly right in some sense, but relativity, general relativity, the idea that space-time is curved, etc., is almost certainly an approximation because the classical theory, we know that classical mechanics is an approximation to quantum mechanics. So in that kind of trivial sense, we know that Newton's laws are not completely true. But let's imagine that we are in the regime where Newton's laws are supposed to be true. Are they still completely true there? So we're not moving at the speed of light or close to it. We're big macroscopic objects. No quantum effects are really evident. There's still a sense in which Newton's laws might appear not to be true. When a ball rolls down a hill, it eventually comes to a stop, right? Because of friction. So in the real world, we are constantly using some version of Newton's laws in ways that are only sort of halfway applicable. So they're not supposed to be the complete description. We can set up, we can talk about a theory of something that is part of the world, but not the whole world. Newton's laws have no trouble talking about a ball rolling down a hill, but you can derive conservation of momentum from Newton's laws. How do you reconcile that? Well, you say the application of F equals ma to the ball rolling down a hill was true, but the kinds of forces there cannot be themselves derived from Newton's laws. You're making some extra assumptions. So there's this sort of more immediately relevant sense in which Newton's laws are completely true only if you're really being comprehensive, only if you're really getting down to the nitty-gritty of all the atoms and molecules and applying them exactly, which in many appropriate cases we just don't want to do. So even in the classical world, even in the world of 18th century physics or 19th century physics, there was a sense in which Newton's laws weren't completely true, but we thought that's just because we weren't doing the full job that we might want to do. Okay, final question. Are the laws of physics themselves laws of physics changing? So we talked about change in the sense of an object changing its position or its velocity over time or its acceleration or whatever. So, but we took the laws. Did I write that correctly? I'm not sure I did. We took the laws themselves to be fixed. So these days in cosmology, in particle physics, in string theory or whatever, it is very, very common to at least imagine that the laws are changing. That somewhere else in the universe or some other moment of time, the charge of the electron was a little bit different, or the mass of the electron. In fact, essentially all modern working particle physicists think that in that sense, the laws of physics did change. Remember, we discovered the Higgs boson back in 2012. The Higgs boson gives mass, the Higgs field that pervades all of space gives mass to the electron because the Higgs field has a value in empty space. The picture that we typically draw here is, here's the energy of the Higgs, we'll call it the potential, as a function of the value of the Higgs field. Here's the Higgs field, and it looks kind of like this, okay? So if the Higgs field were zero, it would have a lot of energy wrapped up in it. But if the Higgs field falls down to this value, the value of the Higgs field is non-zero, but the energy is. And we think that's where we are. And this breaks a symmetry. It could have rolled to the right or to the left. And so that's why we have spontaneous symmetry breaking in physics. But it turns out that in the early universe, when you're not empty space all around you, but in fact there's a plasma of ultra-hot gas and particles bumping into you all the time, this, what we call this potential energy for the Higgs field, changes. It looks like this. In other words, at high temperature, the Higgs field is at zero. That's where it sits, at the bottom of this kind of curve, not the bottom of this double weld potential. And what that means is that in the early universe, the mass of the electron was a different thing. So if by the laws of physics, you mean what physicists call the low energy laws of physics, the laws of physics that have to do with the particles and forces that we see in the universe around us, yes, those do change. We expect that they might change even more dramatically elsewhere, but we think that they do change. But it's kind of like, you know, does the what should I say? Does the speed of sound in water change? Well, yeah, the speed of sound is different in ice versus liquid water versus water vapor, okay? But we don't think that's a profound fact about the universe. We think that there is some essence of waterness underlying the whole thing. I think that most of us think the same thing here. And this is just thoughts. This is not anything we have strong evidence for, so maybe we're all wrong. But I think that most physicists think that even if the laws of physics that we observe, what we call the low energy effective laws, are different from place to place or time to time, there are still deeper laws, meta laws if you want to call them that, but even deeper, more fundamental laws that don't change over time. That the specific particles and forces we see are manifestations of a particular set of arrangement of stuff that still obeys the meta laws of quantum mechanics and whatever it is, string theory, whatever it turns out to be ultimately. But, like I said, we don't know. This is ultimately an experimental question. You'll be happy to learn, if you don't already know, that this is another thing that we are absolutely trying to test experimentally. We're looking to see whether or not the electron has a different mass now than it did in the past. I've written papers about this myself, so this is an example of a very good question. This is the kind of thing we should be thinking about. I hope these videos are helping us all to think about these big questions as time goes forward.